So let's continue with our next talk. The next talk is going presented by our colleague Marcos Eduardo Biersi from INTI, Argentina. And the name of his presentation is New Metrological Resources of Industry 4.0. Marcos Biersi received the Electronic Engineering degree from the Universidad de Buenos Aires in 2006 and the PhD degree in engineering from the Instituto Tecnológico de Buenos Aires, Argentina, in year 2016. In 2005, he joined the Electricity Division of Instituto Nacional de Tecnología Industrial, INTI, the National Metrology Institute of Argentina. Mainly in his areas of expertise and interest are resistance and voltage metrology, width and cryogenic current comparison, low current and surge measurements, the control theory. His current research includes the design of electronic devices for high voltage and current metrology. Marcos collaborates on several joint research projects with institutes and companies from Argentina, North America, and Europe. Furthermore, he's teacher at the Universidad de Moreno since 2017. As well, as I said at the beginning, he's the coordinator of the task force of the Metrology for Industry 4.0 in the team working group 14. Welcome, Marcos, and the floor is yours. Go ahead.
Hello, could you hear me? I am presenting, I don't know if you can see it.
Yes, we can hear you, and we can see your presentation. Go ahead.
So, thank you very much for this opportunity. My name is Marco Biersi, and I am presenting a work titled New Metrological Results for Industry 4.0. The content of this presentation is the following. We have first a project overview. I will talk about the key point, the objective, the traceability chains. Then I will talk about the development and the result obtained until now. Specifically, I will talk about the digital calibration certificate, traceability, in vibration sensor, traceability in multifunction calibrators. These are the two areas where we are applying the digital calibration certificate, and finally the conclusion. So, which are the key point of the project? This is an associated research project funded by the Ministry of Science and Technology of Argentina. We have two partners, High-Tech and INTI. High-Tech is a private company of Argentina. They give a presentation in the last M4DT conference 2 or 3 weeks ago, I think. We are working with them in this project of 18 months. This project involved 18 professionals and a total budget of $335,000. The end of the project is in 2023. So, which are the objectives of the project? We have two primary objectives, and they are focused, of course, in the Industry 4.0. What happened in the Industry 4.0? We have a lot of different data, and we have to take care of the data. In particular, we are interested in the calibration data of the instrument. So for that, you know very well, there exists a lot of interest, international interest, to set up some digital calibration certificates. So the first objective of this project is to ensure the calibration data quality in its generation, the use, and in the transfer between the provider and the client. We apply the digital calibration certificate, and we will apply in two different areas. One is the vibration area, two sensors that are directly installed in a company, in an industry, and the other area is the electrical area, which we're going to be focused on the multifunction calibrators. This is the first objective. The second objective is to reduce the effort to obtain traceability. Nowadays, what we are interested in is that the client can reduce all the cost, the risk to obtain traceability. So the proposal is to bring the standard closer to the instrument and the calibration. In this way, the laboratory that provides the service will assume the risk to move the equipment to the laboratory of the customer. And also we assume the dead time, that means to move the equipment. So in this way, the customer don't need to lose time, don't have risk in the its standard. The price can be the same or higher, but what we are thinking is that some customer in Argentina has many instruments, many multifunction calibrators, for example. If you move just one standard, can be lower the final price of all the service, including, of course, the transport of the calibrators and instrument. So we're going to apply this in two traceability chains. The first chain, as I told you before, is the sensor applied to measure vibration in an industry. So for this, we're going to implement a digital traceability chain from the primary standard at INTI to the sensor produced by Hightech and installed in a company. The work involves a new standard at INTI and also all the procedure that Hightech requires for make the calibration of their products. This is a very interesting example of application of the DCC, because will be an application directly with the end point in a product applied in industry and for IoT, industrial IoT. So I will show you before, next that the DCC will be integrated in the software produced by Hightech, and we hope that this shows to the rest of the company that produce device of IoT or similar application that they can take advantage of the DCC. The other traceability chain where we are working is in electrical for multifunction calibrators. In this case, we are making a new process which is fully automatic to the calibration of multifunction calibrators. This process, this system will be controlled by the software, and the software will read the DCC for the multimeter and also will generate the DCC for the calibrators. In this case, it's quite important, this example, because the calibrator needs more than 100 points of calibration. So the certificate used to be very large. And in this way, we are giving an example of another powerful application of the DCC, where you have very large certificates, calibration certificates. We are also interested in automatic multifunction calibrator, because nowadays this process is semi-automatic here at INTI, and we believe that this can be also be applied in private laboratories. And nowadays in Argentina, we have just one laboratory that can perform this task. So we're interested to create more offer of this service. So, which are the development and results that we are obtaining until now? First, about the digital calibration certificate, we have a lot of different information about that. So I don't going to be to waste a lot of time speaking about the digital calibration certificate. Just a definition about it. It's a document that is transferable, accessible, secure, robust, interoperable, reusable, machine readable, capable of being understood by humans as well as machines, and capable of storing metadata like any other information. We are using the PTB format and in XML file. For example, this is the first page of an actual certificate generated by INTI, where we have all the information about the device under calibration, the dates, and the client, and also about INTI. So how we change this information to the PTB format or the XML file, just in this way. This each of these levels indicates some information. That level is defined by the PTB format. So, for example, postcode means the postcode of INTI in this case, and here we have the information in the middle of the two levels. This is also the is a typical file, XML file, but the name of the level was indicated by the PTB format. Here is an example of how we can express measurement results. Sorry, I have a problem here. For example, if we measure 1 meter of length, first we have to indicate the quantity type, the value, and the unit. And then I can indicate the uncertainty. This is the expanding uncertainty, and the coverage factor, and the type of distribution of the uncertainty. So this is the proof of concept that we are having nowadays at INTI. This is an online platform that is in a server here at INTI, and any metrology of INTI can use it by an Internet Explorer. You can download first the spreadsheets, and then you upload this spreadsheet to generate the XML file and the PDF file. This platform make both, generate both files. The spreadsheet you download are nowadays for 3 different types of calibration: the PT100, accelerometers, and multimeters. Why we do it in this way? Because this is compatible with what we are working nowadays in the service. So the metrologist has to copy the measurement result in the spreadsheet, then upload the spreadsheet to this platform and generate the DCC. In this way, the metrologists don't need to take care about all the libraries, software that the platform requires. So for that reason, we use a server instead to make this like a program that runs in each computer. So the point is how we can apply the DCC from 2 traceability chain. And this is what we are talking about. And this is the first example. This is the vibration traceability chain. It starts in the primary laboratory of INTI with the primary standard. With this, we generate a DCC for the standard of the company Hightech. Then Hightech can calibrate its standard, its working standard, these calibrators, and then with this instrument they give value to the sensor that finally can be installed in a company. All the transfer of data is made with the DCC. So INTI can calibrate the Hightech standard by interferometer method under the norm ISO 16063-11 method 1 and 2. In the frame of this project, one of the objectives is to update this system to a model system 1. INTI already implemented the digital calibration certificate for these accelerometers and calibrators. Hightech calibrated the calibrator 9100 back-to-back by a back-to-back method. We select this instrument because it has an DNC output where we can measure directly the internal accelerometer signal. And Hightech has a 6.5 digit multimeter for this task. So we don't calibrate just the calibrator. We calibrate the calibrator plus the multimeter. And then they have to use in this way because we make the calculation, and in this way we will reduce the uncertainty of the standard, and because we are neglecting the uncertainty of the internal readout or the internal digitizer of the instrument. So, and then Hightech wrote the calibration procedure for all this calibration, and now we already have an XML file for this shaker, this little calibrator. This just can work at 2 frequencies and can be used to perform in situ or remote calibration directly in the where the sensor is installed. Hightech is working to modify all his software platform, in order to integrate the DCC. So when the data measured by the vibration sensor is analyzed, they take in consideration they can correct the data by the DCC, or they can calculate the uncertainty. So the other traceability chain where we are working is the electrical traceability chain. This is, our objective is to create a new automatic system to the calibration of multifunction calibrator. In the signal that you can see here, the magnitude is DC and AC voltage, DC and AC current, resistance, capacitance, and frequency. With this range, as you can see in the AC voltage, we don't try to cover all the range of the multifunction calibrator. We work in the reduced range, but this range is the most important for the industry. So the new system is quite simple. It is based in a high accuracy multimeter and a state-of-art multimeter, and custom-made multiplexer. We call a multivariable multiplexer. And with these two instruments, we plan to calibrate the multifunction calibrator. Nowadays, to make this task, we use all these other instruments. We use a high accuracy multimeter, an LCR meter, an AC voltmeter, a lot of different resistors and shunts, and a lot of different cables and adapters. So why we try to modify this system? First, because this, as you can see here, is semi-automatic. You have to be changing between different instruments. And second, specifically the AC voltmeter is a very expensive instrument, very expensive calibration, and it's quite difficult to think that that the private company of Argentina buy one of these instruments to calibrate the multifunction calibrator, because it's extremely expensive. So for that reason, we are trying to make this automatic, simplified system that can be useful to perform the calibration and can be interested for private company in order to give the service, and with a reduced range, of course. In another advantage of the new system is that it is a transportable calibration system. It's completely impossible to move the actual system to a customer lab. Is a lot of instruments, but these two instruments are very simple to transport. I have to be clear that some resistors are included in the multiplexer box. So in a sense, we are eliminated the LCR meter, we are eliminated the AC voltage, which is the AC voltmeter, which is a more expensive device, and we don't use all the resistors that nowadays are using. In this way, we can implement the remote calibration. This means to carry the standard directly to the laboratory lab, and the metrologist can be in his lab working and controlling the measurement remotely by internet. So since the system is quite simple to use, the idea is that the customer can make the connection and then everything run with the software or can be controlled remotely. So we are building now the multiplexer, multivariable multiplexer, and these are the specifications. The objective of the specification, it has an isolation resistance larger than 1 teraohm. This is important because we are measuring resistance up to 1 kiloohm, and to obtain an uncertainty of 0.1%, which is enough for this application, we need an isolation resistance in the board and relay of 1 teraohm. Then we need a thermoelectric voltage lower than 0.1 microvolt. This also is important to obtain a 1 ppm uncertainty 100 millivolt at DC. I have to be clear, 1 ppm is stable measurement because we are going to make a zero of the measurement. So this is the variation has to be lower than 0.1 microvolt. Then the contact resistance of the relay has to be lower than 1 ohm. This is important because when you measure AC voltage, the strike capacitance of the digitizer can generate some voltage divider, impedance divider between the wire and contact resistance and the input capacitance, and making all simulation. If you have lower than 1 ohm, you have 10 ppm and 20 kilohertz. 10 ppm for this application is very good. The strike capacitance has to be lower than 5 picofarad, and the maximum voltage is 1000 volt RMS and 20 amps RMS. This is the circuit schematic. We are using the front and the rear panel of the multiplexer. The front panel are used to measure current. The rear panel are used to measure all the other magnitudes. And we are using some internal resistor of the multiplexer in order to improve the uncertainty in current. These are the board that we are already finished. This is a digital board that was produced by Hightech. And here you can see all the analog, the opto-isolator, the temperature sensor, and it is connected by USB to the computer. And this is the current board that you can see that it don't have component because we had a lot of problems to buy the component. We need like 4 months to buy some release. Already we have there. This is a crazy moment to buy component, international component of accuracy because you can't find market international. And the interesting point of this board is that the shunt is directly connected by this plug in the board. We have space to choose shunts. These are the shunts for 0.1 ampere, for example. And then here we can connect another shunt of larger current in separate way. Also here we have the possibility to connect another shunt. So inside the same chassis, we can leave the shunt there installed. We already could test one of the board. This is the multivariable board. This board will be used for voltage, current node, voltage resistance, capacitance, and frequency. We test it using a Fluke 5700 calibrator and a HP 7458 multimeter, and we obtained this error. This was a test under the table. The error with and without the board was in DC voltage was lower than 1 ppm, in AC voltage up to 20 kilohertz was lower than 25 pico ppm, in resistance in all the scale was lower than 5 ppm. This is from 1 ohm up to 1 ohm. We expect to have better result even when we have the final system installed. This is the thermoelectrical voltage of the relay that you see previously. This is a very nice picture. You have all the measurement here in the horizontal X. In the left, you have the contact voltage. In the right, the temperature. The green line is the temperature. So we're going to, you can see how the temperature was changed in the board, in a climate chamber, and then how in blue, the thermoelectric voltage of one way of the board was lower always than 0.15 microvolt. The peak that you can see coincides with change of the temperature, and this is produced because the gradient on the board increased the thermoelectrical voltage. So with this measurement, we can be sure that the specification of a low thermoelectrical voltage will be obtained if we want to maintain the temperature almost constant in the board. So the board will be integrated to a software. This is a software that actually is using to calibrate this type of instrument, and it was already updated to control the multiplexer by USB port. You select the instrument to be calibrated, the instrument to the calibrator. You can select the address of both instruments and put some information about the service itself. Then you can select what type of service are you interested to do. And finally, you run the program and you start to see in this spreadsheet all the information. So what we need to do now is to update this system to perform the calculation and then generate the GCC. Tonight, you calibrate the multimeter with this system. You need to then pass the copy the result by hand in the spreadsheet generated by the platform. But the idea is to make this process automatically. So my conclusion, now finishing. Sorry, okay. The digital calibration certificate platform was implemented. It is almost 90% make, and I think that in this beta version will be for a lot of time. Then the partners are working to establish a digital traceability chain from the primary standard up to the vibration sensor. We are now in a very good process to finish this in the 2023. And we are making the fully automatic system to calibrate multifunction calibrator. The multiplex is under construction. We already have the procedure and the software is almost done. So we also believe that in 2023 we're going to be finished this part of the project also. So thank you very much for your time.
Thank you very much to you, Marcos, for very interesting project that you are working. I invite you to do your question in the chat, or if you prefer, you can raise your hand and use your micro. You can feel free to speak in English, to speak in Spanish, please. In the meantime, maybe you mentioned, Marcos, but I don't know if the project allows you to calibrate different models of accelerators or a specific model. I don't remember if you mentioned.
No, when we prepare the DCC, we try to be general for each type of instrument. It's quite difficult, and this is the problem that when we make the DCC, because everything has to be quite standardized. Okay, so the points, the information you give, everything has to be fixed. But what we're trying to do is to think in type of instrument instead of just one model.
Okay, thank you, Marcos. So, any questions?
So, yes, I have a question.
Okay.
I'm Jackson from Brazil. Okay, can you hear me?
Yes.
Yeah. Yes. Yes. The intention is to make another service to like a contract of calibration with companies. Yes, that's what I understand. Make contracts of calibration from companies to make a solution to a company and then make the calibration. And could be starting with accelerators, then perhaps pressure calibrators and so on.
Yeah, the first objective of the project is to have some example of application of DCC. This is the first point. And then for example, the traceability in vibration, what we are thinking is that the company has the possibility also to make all the traceability, internal traceability, to the product that they sell and install. So up to now, we are just focusing these two areas, vibration and electrical, special multifunction calibrator or multimeters. But of course, the DCC in one moment can be synced for any other type of instrument. And in this case, the spreadsheet and the software had to be rewriting for this type of thing. So what we are thinking in the DCC, we are not seeing to apply in all the service of Indy. We are just seeing to apply in the service where we require that. This is because you have a software that can be used, the DCC, or because we have plenty of data to transfer between the customers and the provider, service provider. Okay, I was clear?
Yes.
We are not seeing to apply in all the service of Indy. We are just seeing to apply in the service where we require that.
Can you share the
This is because you have a software that can be used.
They're going to be available in our web page. So just wait after this event, please. Thank you very much, Marcos.
You're welcome. See you.